This video covers the concept of total internal reflection. So total internal reflection can only happen when light travels from a slower medium like water or glass to a faster medium like air. So let's assume that we have this light wave reaching an interface. Part of this wave is going to be reflected, and part of this wave is going to be refracted. The amount of energy that is transferred to the refracted and reflected wave depends on the incoming angle of the wave to the interface. So let's assume that we have 100% of the light energy before interacting with the interface. The majority of the light is going to be reflected, 92%. This means that the remaining 8% is going to be refracted. Let's explore what happens to a wave that has a smaller angle with the normal line. We know that some of the wave is going to be reflected and refracted. But we also find out that the closer the wave is to the normal line, the more the light is refracted. We then see that the incoming angle increases, less and less energy is transmitted to the other medium. Let's look at this idea more closely. Alright, so let's say that we have light coming into this interface, and the light that comes in at what we call the critical angle. When this critical angle or greater is reached, no light is transmitted out of the medium, and instead the light is reflected back into the original medium. No light is able to leave. So 100% of the light goes back into the material and 0% leave. Therefore, the refracted angle is 90 degrees, which essentially means that all of the light once again stays in the original material. The critical angle for water to air is 48.6 degrees, and the critical angle for glass to air is 41.8 degrees. So let's do an example. We have two light waves coming from water and are directed upward toward the air. We want to figure out which one is refracted and which one has total internal reflection. We know that the critical angle for water to air is 48.6 degrees. So if any angle is larger than this, we know that there will be total internal reflection. So let's look at this example on the right first. We know that some of this wave will be reflected, like this. And the angle of 60 degrees is larger than the critical angle. So therefore, no light escapes the water. And therefore, we have total internal reflection. Let's do the example on the left now. We know that the light is reflected as shown, and since 30 degrees is less than the critical angle of 48.6 degrees, we know that the light does in fact escape, and since it is going from a slower to a faster medium, it bends away from the normal line.